Hello, everybody. Welcome to Insider's Guide to the Galaxy. I'm Charles Ennis, your co-host. Chris Vaughan is your other host here. He's got a great show ready for you on magnitude, so I'm going to hand this over to him. And Chris, take it away.
Thanks, Charles. Hi, everybody. So the thinking here about covering or talking about magnitudes and brightnesses is because it's something we haven't done before, but also because it's galaxy season and there's going to be a connection to that as we get kind of deeper into it here. So let's kind of start out. I'm going to do what I did last time where I basically talk a lot, don't show too many visuals until we get a little bit deeper in. But what I will do is I will share my screen and let everybody enjoy the stellarium scenes here while I talk. There we go. I'll just do this because then I can point to a few things in the stellarium. So we're going to be talking about brightness. Brightness is how we perceive the light from objects arriving from the distance. Generally, we're going to talk about light in visible wavelengths, which the human eyes can detect. And what really we're talking about in a sort of a physics terms is the flux or the energy per unit area that's entering our pupils or our telescope objectives or our detectors, whatever we want. And basically we're talking about that flux measured in watts per square meter, for example. Now, the sun's output in the EM spectrum arriving at the top of Earth's atmosphere actually puts out about 1.321 to 1.412 10 to the third watts per square meter. So it varies because of Earth's elliptical orbit. We're closer and farther from the sun at different times of the year. So that's about 14, think of it about 1400 watts per square meter. In contrast, the star Sirius, which is down here visible in the stellarium screen right now, we get about one times 10 to the minus 7 watts per square meter, or about 14 billion times less flux from the star Sirius. Now, when we start getting into measuring these fluxes, these brightnesses, we start getting into something we call photometry. So photometry is adding a number or numerical measurement to those. It was basically developed, the process was developed essentially in the late 19th century, first using something called a bolometer. I'm not going to get too much into what that was at the moment, but we'll come back to that word bolometer or bolometer in a little bit. So the brightness that we're measuring is what we're seeing, its apparent brightness. It's the way things appear to be or how bright things appear to be to our eye. But that's not necessarily the brightness of the actual object. So objects have their own intrinsic brightness, which is the amount of light or energy that they're emitting. And it's only, after that light has journeyed to our Earth and entered our eyeballs or our detectors that we can actually put a measure on how bright that object is. So the light that's coming from the object or the energy coming from the object, we call its luminosity, again, measured in watts, if you want to get technical about it. And the distance we're seeing it at affects the brightness that we perceive. It's the idea of if you're close to car headlights, they look bright to you, but if the same car headlights are at a distance from you, they look much, much dimmer. And the reason that brightness decreases with distance is because the light is being emitted radially all around the object. And that light is actually, falling upon different spheres at different radii from the object. And as you get farther from the object, the same amount of light is spread over a bigger area. So the density of the energy, the density of the light decreases quite a bit by the square of the radius. Now, there's another factor that causes things to look dimmer than they really are, and that's extinction. And we'll come back and talk about extinction a little bit later. So now, if you know the object's inherent luminosity or its intrinsic brightness, and its distance, then you can get two of the three parameters and work out the other. So if you've noticed its distance and its apparent brightness, you can calculate how luminous it must really be in reality. Or if you want to know its distance, if you know its intrinsic brightness and compare that with its apparent brightness, then you can calculate or estimate how far away it is. And that brings the concept of standard candles, using things in the universe that we know how bright they should be compared to how bright they do look, lets us guess or estimate how far away they are. Things like that were able to help us figure out the scale of the galaxy, the scale of the universe, things like that. And there are formulas. If you want to go ahead and look up the formulas for flux and luminosity and distance, they're to do with trigonometry. You can go ahead and look those up. Now, extinction. Let's get back to extinction for a second. So extinction is the way things are dimmed. Either when the light has been passing through some interstellar dust or gas that might be scattering the light or filtering it out and dimming its intensity, or it could be actually dimmed by the Earth's atmosphere itself, which we're always looking through. Now, one fun fact that you may not have heard is that the double cluster, which is a famous naked eye binoculars object, it's actually about 4 times fainter than it really should be due to extinction by the material of the Milky Way in between us and the double cluster. So if it weren't for that extinction, they would be far more bright in the sky. So objects tend to look dimmer when they're lower in the sky. I'm just going to bring up some markings here on stellarium just to show you the meridian. Where's my meridian? Here we go. Let's do this. Let's turn around and face south an example. So that meridian is the north-south line. Objects rise in the east, they cross the meridian and set in the west. And when they're on the meridian, they're at their highest in the sky. And if you click on any object that's in stellarium here, you can see here, there's a star Tania Australis. Stellarium reports its magnitude as 3.05. And then it says here in brackets, reduced to 3.18 by 1 air masses. So it's very, very slightly less bright than it really is due to the impact of the Earth's blanket of air. Now at 90 degrees, we're looking at the minimum amount of air in the sky. But if we get down something lower in the sky, something say in the 60-degree elevation range, there's the star Regulus. Its magnitude is 1.35, but it's actually what we see is a star that's shining at magnitude 1.5 because it's reduced. We're looking at about 18% more of a blanket of air when we're looking at that star. And by the time we get to say something in the 45 or 40-degree range altitude, here's the star Alphard in Hydra. It's about a 2 magnitude 2 star, but it's reduced to magnitude 2.17 because we're looking at about 69% thicker blanket of atmosphere. And you can see this number is rapidly climbing. By the time we get to 30 degrees, we're looking at double the amount of air. And then when we get down to something in the, say, 15 degrees above the horizon, you're looking through almost 4 times as much air. So that's the reason why astronomers always suggest that when you want to see something that's on the dimmer side of things, catch it when it's on the meridian, because that's when it's at its highest for you in the sky. So Charles can put the link that I found to a nice article on extinction that you can take a little bit of time to take a look at that. Now, that doesn't count the other things that get in our way as astronomers, things like smoke or pollen or plain old clouds. Any of those things will also diminish the brightness of objects we see in the sky. And then there's also transparency, the cleanness and transparency of the sky that can get loaded with moisture and reduce its transparency. So all of those factors contribute to the actual brightness that we see things. Now, as one final twist on all this, another way that things can look dimmer than they actually are is if they're receding from us, then their light can be redshifted away from the visible spectrum into the closer to the red or infrared part of the spectrum. And that's what we're doing when we're using Hubble Space Telescope and the James Webb Space Telescope to actually look at objects that are reddened and dimmed because they're so far away from us and they're receding at such a high rate. Any questions so far?
No, it's quite on the question front so far.
All right, cool. All right, so let's get a little bit of background on the magnitude system and what we mean when we talk about the magnitude of objects in the sky. So way back in the around the time of the year 200 AD, 200 BC, I should say. The Greek astronomer Hipparchus, he's credited with the concept of assigning rankings or brightnesses to the stars in the sky. Now, we know this because even though Hipparchus's writings have largely been lost to the annals of history, some of his folks that came along after him referenced his work, used his work, built upon his work. So the Roman by the name of Pliny the Elder, who lived around 24 to the year 79 AD, he reported in some of his writings of Hipparchus's work. So Hipparchus produced a catalog of about 850 stars. And in his catalog, he assigned their brightnesses to a ranking system. And what he did is he said, okay, he's going to look up in the sky, didn't have a telescope, didn't have anything but his plain old eyes. And he said, the brightest stars I'm going to assign as first place. They're the brightest. We're going to call them the rank number 1. And then we're going to go, maybe there might have been top 20 stars in the sky from where he could view the sky from. The next brightest stars he assigned rank 2, call it second place. So first place stars, second place stars, third, fourth, fifth, and so on down the list until he said he reached the limit of his observability and he called those stars rank 6. So he had rankings from 1 to 6, from the brightest stars he could see to the faintest stars he could see. Now, there's an interesting fact about human biology that when we look up at, we tend to sense things on a power law basis. So we sort of inherently think of things as half as bright and half as bright as that and half as bright as that. So there actually is a kind of a scale that we use, and that kind of contributed to the way this all worked. Now, Charles can put a neat link into the chat. So we thought Hipparchus's catalog was completely lost, but around 2021, researchers who were doing multispectral scanning of ancient documents, a document called the Codex Climaci Rescriptus, detected an underlying text below the sort of visible text. And it turns out that it may be a star catalog or a piece of a star catalog. And we were wondering, or researchers are wondering if it might be part of Hipparchus's, because it's in ancient Greek and it kind of fits the bill with what we expect. So that's a cool article if Charles puts that in the chat.
Yeah, Chris, I think they have confirmed that it is from his works, and they are busy scanning other documents to see if they can find it. This is something that was called palimpsest, where you had a scroll and you didn't need it anymore, so you scraped it to get the stuff off, and then you wrote something over the top. But with modern instruments, you can read the original text, and they reused one of his texts to do these church scripts.
That's amazing. I love stories like that. It's cool. All right, so here we've got the basis of a way to kind of categorize the stars in the sky. Things go on, people keep looking up. We get to the time of Ptolemy, another Roman astronomer. He lived from 100 to 170 AD, and he published a great work of astronomical research called the Almagest. Lots of us encounter the Almagest when we're doing outreach and research on topics in astronomy. And it was broken up into a number of different volumes on different aspects of the sky. And his volumes 7 and 8 deal with the stars. And what he published in that volume was a list of 1,022 stars, which would have built on Hipparchus's 850. So he's sort of adding another couple of hundred to that. And he noted the stars' position, the constellations that they were in, and he reported their brightnesses using the same system that Hipparchus had initiated. And I found a link to a neat study. It's an English paper, English language paper, analyzing the contents of the Almagest. And if you kind of scroll down to page 120 in this document, a little bit past that, you can see the list of stars from the Almagest star catalog. And it's really fun to go through that list and see, there's Vega, magnitude 1, that sort of thing. Even though Vega isn't 1, we'll come back to that in a second. All right, so things went on for quite a while, jump well ahead in a millennium. We get into the 1600s. Galileo starts looking up at the sky with his spyglass, And what does he discover? More stars. He realizes right away that he can see far more stars that are visible to the human eye. And so he had the presence of mind to say, well, we've got rankings down to 6. Let's just carry the story on. We'll call the brightest of the new ones that I can now see on my telescope, we'll call those of the 7th magnitude. And I think that's probably the first reference to the word magnitude as being used for stars in history. And then as time went on, telescopes got better. We started to look deeper and deeper, and we just kept adding to the numbers. So 7, 8, 9, and so on down the road. So that's great. Things are going well. We're discovering more, looking deeper, using that, extending or extrapolating that same system to deeper and deeper objects. But things got a little bit tricky after a while because we started getting a lot of astronomers working independently all around the world with their various instruments. And they're compiling their notes, they're publishing lists, they're producing catalogs. At some point, somebody had to get organized and assign a structure to it, because if somebody wanted to embark on a study using someone's catalog, they would like to be able to be consistent amongst the different sources out there. Also around the time we got to the, say, mid-1800s, the idea of formal photometry, or measuring the brightness of objects, came into usage. And so we now were able to actually measure the brightness of stars one by one by using some of these techniques. So it would be only natural to assign those measurements to various star catalogs. So around about that time, an English astronomer by the name of Norman Robert Pogson, he was actually working in India at the Madras Observatory, and he somehow noticed, because he now had access to measured brightnesses of stars, that Hipparchus and Ptolemy's magnitude 1 stars happened to be almost exactly 100 times brighter than the magnitude 6 stars. So that difference of 5 integer amounts from 1 to 6 equaled a brightness variance of 100, factor of 100. And so it was only natural for him to think, okay, let's standardize this by assuming that the difference is exactly 100, and we'll make each step along the way the 5th root of 100. And when you work that out, that Pogson's ratio that he came up with, it turns out that if you multiply 2.512 times 2.512 times 2.512, 5 times, you get 100. And so each step in the magnitude scale represented a difference in brightness of 2.512, or 2.5. So a magnitude 2 star is 2.5 times fainter than a magnitude 1 star, and down and down and down and down. Now, because it's not a linear scale, it's not logarithmic, it's power law, it's something sort of like a logarithmic scale. That means that a magnitude 2.5 star would not fall in the middle of the brightness range between a mag 2 and a mag 3. You actually need to go to, I think, something like, it's actually only about 1.5 times brighter or fainter to go to the half step between the magnitude integer amounts. Now they wanted to assign, a reference star to anchor the system that they came up with. So they figured, let's use Polaris. If Polaris is visible by everybody, in our part of the world that's doing astronomy, nobody worried about the southern hemisphere necessarily yet. But they figured Polaris was visible by all these natural philosophers and astronomers. Let's assign it the magnitude of value of 2.0. So then we'd have the stars that are brighter and the stars that are fainter anchoring our scale. But then somebody came along and realized that Polaris was variable, that it varied in brightness. So that didn't really make it suitable for an anchor for the scale. So they decided to make the star Vega the anchor. Let's see if Vega, we can get Vega to come up here later in the evening here. There we go, there's Vega. So Vega was actually assigned, even though originally Hipparchus had given it a ranking of 1, because he was just saying everything bright. Now we had a numerical measurement of its brightness, and on Pogson's scale, we decided to give Vega the value of 0.0 to anchor the scale, and everything's referenced to that. And interestingly enough, of course, stars emit light at different wavelengths. We're used to seeing them in the visible range of wavelengths, the human eyeballs, but Vega's emitting light in the ultraviolet and in the infrared range of the electromagnetic spectrum. So a Vega was actually its output, and all of those different wavelengths were given as the 0 point for all the respective scales in other wavelengths of light, so not just the visible light. And even using Vega is probably not completely satisfactory to physicists. So what they decided to do was formalize it even more and basically say that the light output by a black body at 11,000 K would be the zero standard, and Vega happens to be very close to that light output. So cool, we're ready to go. We got lots of ways to assign numbers and brightness values, magnitude values to the stars in the sky. And then a supernova comes along. And supernova is outshining all the other bright stars in the sky. Now what do? We can't put it in the one end of the range, so we've got to have a way of identifying things that are brighter than Vega or the brightest star. Okay, so what we're going to do, we're going to make it 0, -1, -2, go the other direction on the number line. And that, of course, allowed them also to include things like the moon and bright planets and the sun. So when you put all that together, you get this nice scale that ranges from, the sun, which is magnitude -26.7. Again, each of those integers all the way down to -26 is a 2.5, 2.5, 2.5 factor. You can do this, you can do the math on it. I think it's something like some trillion billion times, the sun is something like some trillion billion times brighter than the dimmest object, which tend to be the things we pick up in the Hubble Space Telescope or the James Webb, which is down at magnitude around +31 or +32. So that's the crazy kind of range that we get. Here's actually a nice page that was put together by the Calgary RASC using a stellar magnitude scale. I have a feeling that this diagram might come from Sky and Telescope, even though it doesn't say so here. But here's on the left, you've got the numerical values of magnitude. You've got Vega anchoring in the center here. You've got the plus magnitudes. So plus means I'm in first place, I'm in second place, fourth place, eighth place. I'm down the list, so I'm not as bright or important, all the way down to magnitude 30 plus. And then heading up, beyond Vega, we get Sirius, which I guess is a little bit brighter, of course. Then we're getting the bright planets, the moon at different phases, things like bright meteors, other objects, and then fireballs, and then the sun at the other end of the scale. So I'll pause for a second, let everyone catch up, see if they had anything to ask me.
No questions lurking in the chat at the moment.
Let's see if I can open up this link here. Okay. So when I'm writing about astronomy and I'm wanting to tell people to look at, say, Jupiter next to Venus and giving them a sense of what to expect, I want to be able to say to them, if I say, Venus's magnitude is this and Jupiter's magnitude is that, that's maybe not helpful to very many people, to laypersons especially. But if I say, well, Venus is going to be 5 times brighter than Jupiter, that's something that they can make sense of. So what I like to use is some of these calculator tools, and this is a nice one that I like to use quite a bit. Charles can put the link in the chat there. And this is great. You can just go down here and choose magnitude difference to brightness difference. And then you just type in the magnitude value of the first object, magnitude value of the second object, and it'll actually give you the difference in magnitude, just subtracting the two numbers, but it'll also calculate the brightness difference. So if I take, Vega as the first object, and I take the star Sirius as the second object and calculate, then it turns out that Sirius is about 3.5 times brighter than Vega is. So it's a handy tool. I like to use that one all the time. All right, let's carry on here. So if you're looking at the brightness of objects, so let me just pick here Vega and bring up the numbers that Stellarium shows. You can see here that the information that Stellarium, for example, will show you will vary according to how you've configured the software. And I've got mine set to show a little bit more than the defaults. If you want to see some more details, you can go into the configuration window, which I'll pop open here. Let's see, I think it's under the information tab. then you can actually choose between the default, minimum, none at all, or customized. And you can see I put check marks in beside some of the various things that I want to show, including things like the visual magnitude, the absolute magnitude. And I think I use the additional information is going to give me things like surface brightness, which we'll come back to a little bit here. So now the magnitudes reported by an app like Stellarium or some of the other apps like Sky Safari are going to be basically the visual magnitude, you know, the value or the brightness to the human eyeball range. And if you're looking at, say, the variation of brightness of a variable star on a chart produced by the American Association of Variable Star Observers, the AAVSO website, we talked about that earlier this year. Then that's going to be the brightness or the magnitude of the object at a wavelength of about 555 nanometers. That's basically the peak of the human visible range. And interestingly enough, that's the color of green screens. So that's what green screens are. They're made at that color, that 555 nanometers. There's another system called the UBV, where you can actually get the magnitude of the object in the ultraviolet, which is 350 nanometers, and then you can get the B in the blue region, which is at 435 nanometers. And so you're getting green, ultraviolet, and blue measurements of the brightness of an object. And that by combining and mixing and matching the U, the B, and the V, you can get what's called the color index of the star. So if you're looking in Stellarium, you click on a star. Down here, you can see here under absolute magnitude, we've got the color index, the blue minus V equals 0. That's because, remember I said that Vega, no matter the wavelength, it's the anchor point. So it's going to be 0 across the board. But if I were to pick, say, Capella here, Capella is going to give you B minus V of 0.79. So it's basically a measurement of the color range that the star can be. Now, back to that word bolometer or bolometer. So if the magnitude of an object has been measured across the visible wavelengths that it puts out, then that magnitude value is going to be called the bolometric magnitude. All right, so now just sort of wrapping up this topic of magnitudes, the way I like to remember or use the rules of thumb for this are the larger the magnitude number in terms of the plus numbers, means they're first place, they're the brightest, second place is weaker, less bright, and so on. So the numbers get smaller as you get dimmer. And then things that are brighter than that, we just have to use negatives because we're sitting on a number line and we've got to go to the brighter range of it. Each integer value difference in magnitude is 2.5 times factor in brightness, and adding or subtracting a half magnitude is roughly a kind of a 1.5 times brighter. All right. Questions? We're good?
We're good. People were asking about the links, but they're all coming up in the chat. So I think we're on top of that.
All right. So let's talk about absolute and apparent magnitude. So as I mentioned, apparent magnitude is the apparent brightness, how things look, and the brightness that we measure, say, on the ground from Earth. Now, we do standardize that. What we tend to do is we try to measure the brightness at the object as if it was at the zenith, so at the minimum of impact of the Earth's atmosphere, so sort of the zenith, and on a moonless night, basically. Now, the intrinsic brightness or luminosity of an object lets us talk about the absolute magnitude. So how bright the object would be if you could see it at the same distance as all the other objects in the sky. And what astronomers have decided to do is they have decided to convert the luminosity to an absolute magnitude, which is how bright the object would look if it was sitting 10 parsecs away from the Earth, which equates to 32.5 light years. Astronomers like to use parsecs. but it's 3.25 parsecs or light years per parsec. So it's 32.5 light years away. So in other words, if we could take every star we're interested in and park it at a distance of 32.5 light years, how would they look different than they look right now? And it's kind of amazing to think about it. So let's go back to earlier this evening here. Here we go. Bring this back. We've got the remains of the winter sky setting in the west here. And we've got things like Rigel and so on. So if we can move all the stars to the same 10 parsec or 32.5 light year distance, what do you think the brightest star in the sky would be? Well, which one would look brightest? Anybody want to put any guesses in?
Yeah.
The answer is Deneb. So Deneb, if it were at 32 light years, it would be about 100 times brighter than Venus in the sky. That's crazy. After that would be, let's bring these up, the star Wezen and the star, which one's Aludra? Is it this one? Let's see, Aludra, which one's Aludra? So Aludra and Wezen in Canis Major would be the next brightest after Deneb. They would be, yeah, and after that you'd have Alnilam, which is one of the Orion's belt stars. So they would all be brighter than Venus in the sky. Polaris would, let's see, almost match Venus, again, at equal to Venus at about magnitude minus 3.4. Sirius would barely look as bright as Castor looks right now. And our sun would be at magnitude plus 4.8. I think I've got a neat spreadsheet. Let me just open up the spreadsheet and show this one. So I actually made a list here. Let's see if I get this. Here we go. So for fun, I made this list and took the brightest stars in order of their apparent brightness. And then I can resort this by their absolute magnitude. So if I click this, data, sort, let's see if I can make this work. Sort by absolute magnitude. And there you go. There's Deneb, Aludra, Wezen, Rigel, and so on. So if anybody's interested in having a copy of this, doesn't help you for observing, but it's kind of a fun thing to think about. Okay, what else have we got? So in terms of, literature, if you're reading up about magnitudes and brightnesses, typically we use the capital M abbreviation for the absolute magnitude. We use the lowercase m for the visible magnitude or the apparent magnitude. Sometimes you'll see them add the letter V, subscript V or viz, to indicate that it's the visible magnitude. If you're measuring or detecting the photographic apparent brightness of things or magnitudes of things, you'll often see MP to indicate that it's a photographic brightness, which tends to be biased towards the bluer side of the spectrum. One last thing on absolute brightness. So we're not going to take the brightness of a solar system object. We're not going to take a solar system object and stick it out in 32 light years because we're not going to see it anymore. So if it's a solar system object, a comet, an asteroid, a planet, the default is to set it to 1 astronomical unit. How far away would it be if it were one astronomical unit away? All right, let's talk about limiting magnitudes a little bit. So for visual observers, I talked about wanting to look at objects when they culminate, when they're highest and least extincted by the interfering Earth's atmosphere. We also have a result of that is that we are limited in how faint of an object we can see, given our own circumstances, where we live, what equipment we've got, and so on. And so we get into the concept of, limiting magnitude of an object, or how deep can you go in the sky. So there's limits to how a human eye can detect, and then there are limits to what an instrument or a telescope can detect. And if you grab your observer's handbook and go to page 54 or so, there's a nice little article in here about all the, the mathematics and physics around magnitudes and limiting magnitudes. So if you want to go deep into that, there's references in the handbook for that. Now, one of the main factors, of course, is how bright is the sky, because the brighter your sky is, the less dim objects that you're going to be able to see. So we have a term we call sky brightness or luminance that measures the brightness of the sky. And Charles has got a handy tool in his hand called a sky quality meter. And the sky quality meter actually measures the brightness of the sky, typically at the zenith. And the measurement unit is magnitudes per square. Is it per square arc second on the sky quality meter? I think it should say on there. Yeah. So
it's right there. It's just a little handheld object. It's quite easy to use, and we use it to regularly scan our skies up here. You just point upwards and press a button on the front here, and it'll beep, and then the reading will be in the end here in red. So you can see it in the dark and not ruin your night vision.
And if you got one, you want to make a note, because it'll let you, for example, track to see, track whether your sky is improving or deteriorating over time, if you've logged that. If you want to pitch your municipality on doing a better job at curbing light pollution, it's nice to have some of these measurements and some historical data around that. But at the same time, it's also a handy tool to use to figure out what what's possible for you to see, in order to set your sights or set your goals on your observing programs. And we can get into that a bit next. So it turns out that if you live in a big city, sad to say, your limiting magnitude is probably going to be something about like magnitude +2, which is about 15 stars, and maybe some, and some bright planets and things like that. In a small city, you might get to magnitude 3, which is about 50 stars or so. In the big city suburbs, you get to magnitude 4, you're getting into, say, 250 of the brightest stars in the sky. That's kind of it. So, in some of those cases, you can't even see a whole constellation. You could just see the sort of the biggest, brightest parts of it. The ideal limits under perfect conditions, moonless night, looking straight up, I think a human eye can get to about magnitude 6.5. And, everybody's different. Some people will do better, some people will do worse. And again, it also depends on, how transparent your sky is, but, kind of near the theoretical limit would be about magnitude 6.5. I think that's around 2,500 stars of the stars that are up. So, about 5,000 of the stars in the sky, if you count the bowl above you at that time, and then, the bowl under your feet at the other time of the year.
The number actually for both hemispheres is closer to 4,000 for visible stars in the perfectly dark sky.
So it's a little bit less than the 2,500, maybe closer to 2,000, I guess.
No, I mean 4,000 in each hemisphere, so it will be 8,000.
Oh, really?
Yeah.
Okay. Well, that's good news. Now, there are superhuman astronomers around, people like Stephen O'Meara, who's known for his eagle eyes, who claim to occasionally get to see down to, say, magnitude 8 under very good conditions. So if you're lucky enough to have that pair of eyeballs, great, that's good. Most of us are limited to a range. Now, in terms of the sky quality meter, the actual number that you're measuring, I think typically among the best conditions you can ever expect to get is a number of 22 magnitudes per square arc second. That's about as dark a sky as we can get here from the surface of the Earth. There are factors that will always make a little bit of glow in the sky. There's a sky glow phenomenon, things like that. So we never get a truly dark sky. So about 22 magnitudes per square arc second is the limit. What I'm going to do is I'm going to open up this Bortle scale chart that I made here. See if I get this up. Okay, go and bring this across. So if you've looked at light pollution maps, you've seen the color-coded maps and perhaps the various classes, the so-called name for the Bortle scale. Class 1 and 2 would be excellent dark skies. The naked eye limit, as I said, some people claim 8, so we'll put 8 in this chart, but basically kind of in the 7 to 8 range for truly dark skies. And the mags per square arc second numbers you can see here are topping out at 22, about the best you can get. Most of us are used to the range in the middle. We've got rural or brighter rural skies, class 3 and class 4, where we can get magnitudes, in the 6.5 to 7 range. And here we're getting in the, 21 to 21.5 mags per square arc second. I'm going to come back to these numbers here in a minute. So I have a bit of method to my madness here. By the time we get down into the suburban skies, we're getting into class 4.5 and 5. And those are going to be the yellows and oranges on your map. Here you're looking at the kind of magnitude 5.5 to 6.5 and numbers like 19.25 to 21. And then we get into the suburban conditions where we've got, really the brightest stars. So magnitude 4.5 to 5.5. And then the sort of city skies where we're getting only the brightest stars that we can really see. And by that point, you're getting into mags per arc second in the range around 18. So call that 18 a kind of a background. And if you want to see things in the sky, they've got to be brighter than the background of those sorts of numbers. Now, stars is pretty easy. It's not that much of a problem because, the stars are bright. You can put a telescope or binoculars on them, and you can reveal far deeper, richer universe in a binoculars and telescopes than you can with your naked eyes, because you're going to see their light enhanced and magnified, and you can go far deeper. But what do we do when we're talking about extended objects, deep sky objects, nebulas, galaxies, star clusters, things like that? And so here's where things get a little bit interesting. So typically what you'll find in an app like Stellarium, I'm just going to bring up some deep sky objects on here. And since it's galaxy season, let's just sort of zoom in on the Leo Virgo area. Talk about some of these. I'm actually going to put on here we go, equatorial map. So here you've got the colored symbols and the labels beside some of these colored symbols for the more prominent Messiers and other galaxies in the springtime sky. And so galaxies are, famous for being extended objects. They cover a patch of the sky. And typically when you're looking at the brightness magnitude associated with a deep sky object like that, you're going to see here it says the Messier 66 galaxy is a magnitude of 8.9. And you think, oh, 8.9, that's within my limits for my location. I should have no problem seeing that. But the problem is that that's assuming that all the light from that galaxy has been squeezed down and equated to a point source, or what a star would put out. So the magnitude 8.9 would be all the light you'd see from a star of that magnitude. And that's not how it works. The galaxy is spread out, extended over an area. And so what we have is an integrated brightness, where basically we say this little piece of the galaxy is giving us this much light, adding it all up, adding it all up, adding it all up, and we can come up with a number that's 8.9, but in reality it would be a lot harder to see than a magnitude 8.9 star would be. And so they use photometers and things like that to scan across these extended objects and tally up the brightness and produce the lists of the data that are used in things like Stellarium. What's an easier, or perhaps a better or more realistic number to use is something called the surface brightness. Now, I got into a bit of trouble in my articles in Sky News because for a long time, I was saying that a galaxy was easier to see because it had a high surface brightness. And what I meant was that it had a high apparent brightness, that it looked brighter, or we saw it brighter because of things like it being edge on and its light being concentrated into a smaller area, which meant it was more apparent in the telescope. And I got actually a letter to the editor saying that I shouldn't be using surface brightness because surface brightness is actually a different thing. And so we can talk a bit about what surface brightness is. So surface brightness is actually a very handy number, but what it means is you take the total output of the object, and then you divide that by the area subtended by that object. So it's kind of working in reverse of the integral, but it's not quite the same because the surface brightness reported by an object will depend on the characteristics of it. So if a galaxy, say, has a bright core and a very faint halo or spiral arms around it, the surface brightness averages all that together. And so it might seem that its surface brightness suggests it's brighter than it really is. But the good news is that if you've got a small telescope or maybe not perfect sky conditions, you'll be able to see the core of the galaxy, if not the dim parts. So the surface brightness value is still a handy amount. So what do I mean by this? So for example, if I take M66, you can see that the magnitude number is 8.9, but the surface brightness is 12.6. If I take M66, it's 9.3, but its surface brightness is 12.36. So even though M65 is a half a magnitude fainter than M66, in the telescope, they look about the same brightness because their surface brightness is about the same number. Whereas the hamburger up here, its magnitude is 9.5, which is quite a bit less, but its surface brightness is 12.79. It's a little bit less than the other two. So definitely when you're looking at the triplet, sometimes you'll see these two quite equally and have a little bit of trouble seeing the hamburger without looking a little bit more closely at. So let's do another couple of these. Let's go up to M81 and M82. So these are great ones. These are great objects to look at if you live in the suburbs, because even your backyard telescope on the driveway is likely to be able to see M81 and M82. Look at this. So M81, the magnitude is 6.9, surface brightness is 13. M82, magnitude 8.4, surface brightness is 12.34, half a magnitude better. So actually M82 is a bit easier to see in your telescope than M81 would be. So if you're planning, what you want to look at in the sky, or if you're surprised that you're having some trouble, maybe pay attention a little bit to the surface brightness number and see what it's saying. So for example, here's that lion's tongue, that NGC 2903 that we highlighted in the finest NGCs a little while ago. This is a great little galaxy because it's a magnitude 9 and its surface brightness is 12. It's better than the Leo triplet and arguably could be even considered better than the M81, M82. So it's amazing that it's not on the Messier list, but it's a great target. I recommend folks take a look at it. Let's see, a couple more thoughts, and I'll open up to some questions. So filters are effectively dimming the sky, and they're changing that threshold so that your extended object will stand out better against that threshold. Basically, the way it works is that if you use your sky quality meter, or if you happen to know the luminance in your area, then you can take that number, and as long as an object is, got a lower number than your sky quality value, or within at least a couple, 2 or 3 below that, you should still be able to see the object. Again, there's a nice content or story written up in the Observer's Handbook about all of this if you want to really dive into the thing a little bit deeper. The other thing is, the other aspect of that, and we've mentioned this before, is that's why you don't want to over magnify when you're looking at galaxies. Certainly when you're hunting them down, you want to use low power. Typically the galaxies that we're seeing in spring season are bigger than you think they might be, so they'll sort of show up at a low power field. But because you're not stretching their light over too big of an area by zooming in on them too much, then they'll retain a little bit of that, bright blob characteristics of them. Questions, comments?
Somebody is asking for SQM choices, and I see somebody is, I've got a unihedron unit here. So that's a good one to use. I'll put the link for their website in here.
Yeah, and you can actually, you don't necessarily have to measure it yourself. There are maps, light pollution maps and resources that you can sort of get, you know, averages sort of submitted by people, the Globe at Night people and things like that as well.
Everybody is just patiently listening in the background here. So, we had all of the links in there for Ptolemy's Almagest is an interesting thing because there's like over 1,000 stars in there, but what you get is not names. Only 10 of the stars actually have a name. All of the rest are descriptions. This is the right elbow. This is the nose or whatever. So it's all descriptions of where these things are in the sky.
And that's how isn't that funny how the roundabout method? So then the pre-Islamic astronomers took the Almagest, took those descriptions and gave Arabic expressions for the elbow of the camel or something.
Yes, they did.
And then that got adapted into the Arabic star names that we use today.
Right, got translated or more often mistranslated into Latin, and then
Right.
the names that we now use. So yeah.
So things like Alberio and Denebula, all those names, when you read up on what they mean, you'll find that they're all third, fourth generations back from those original descriptions. Yeah,
That's right.
It's a lot of fun. So yeah, so interestingly, obviously when you if you're using Stellarium or an app and you click on a star, you're going to see alternate designations for those stars. Typically, you're going to see HIP, and that's for Hipparchus, not named after him, but named after the spacecraft, the space telescope. That is actually its job is to measure photometrically the positions and brightnesses of all the different stars in our Milky Way. So that's the Hipparchus designation. Yeah.
There's
All right, let me just set up
catalogs. And on Stellarium, it's got the HD catalog and it's got ARP and all kinds of others too.
Yes. All right, let's do this. I'm going to pause here and go here. And let's do some finest NGCs. On my shared screen again. Share, here we go.
Oh, before you get rolling there, somebody came up with a question. They are asking why 32.5 light years for magnitude is the question. That's that parsec versus light years thing.
Well, it's more to do with the parsec value. So the parsec is a parallel arc second, and it's the apparent offset that a star will move, using the parallax method by looking at its location at one point in the year when the Earth is at one side of the solar system in its orbit in the solar system. 6 months later, the Earth is orbited halfway around the sun. We're now viewing that star from 2 AUs away, and the star that's moved by 1 arc second, if you do the math, that's 3.2 light years. That star must be 3.2 light years away. So astronomers like to use parsecs instead of light years. Not sure why. That's just the way it is. So the 10 is just, I think they probably said, well, if we put all the stars at 1 parsec away, they would just be all grouped at one end of the range. By putting them at 10, we at least get some range in the values, but not sure. So most of the reading I said, people said words like the arbitrarily chosen 10 parsecs number. So it's somebody decided and that's what it is. I don't know. Does that answer the question? I hope so.
I think so.
All right. Let me just I'm going to bring up my bookmarks here. See if I get here we go. Okay, good. So as I mentioned, the last couple of sessions, we're deep into the springtime finest NGCs, thanks to Alan Dyer, who produced the list that's in the Observer's Handbook. And because most of these objects are faint, fuzzy galaxies, we don't really have a way of highlighting certain sets of them at different times of the spring, because you know, we're going to have weeks where the moon is bright, weeks where the moon is dim. Basically, we're going to just assume that the sky is dark and you're going to chase after them whenever you've got a clear moonless night to go after them for. So I'm just sort of, instead of, you know, highlighting them in that order, worrying about what the moon's doing, I just essentially took them, the ones in the west, and I'm just sort of marching east through the list of spring objects. And what I'm going to do this time is I've got this set of objects here that are highlighted, and our friend or your friend, when you're finding these, is going to be the same friend you use if you want to look at the Virgo cluster or Markarian's chain of galaxies, and that is the star Denebola. Let me just bring up some star names here so there are a little more of these here listed. There we go. The star Denebola at the tail of Leo the lion, or the nose of the mouse if you want to turn that constellation around the other way. And then Vindemayatrix, which is one of the arms of Virgo. And these two relatively bright stars are usually very easy to find in the sky on a night that you're going to be looking at galaxies anyway. And if you make note of the kind of the, you know, line between them, that's going to help you navigate to a lot of these objects. So I've got the stellarium set to 10 p.m., which is, you know, when the sky is truly dark around this time of the year. And first up here is NGC 4762. It's also known as the Paper Kite Galaxy. 4762, that's this one. The reason I put this one first is because it's tucked in close to Vindemayatrix. And if you're doing that trip from Vindemayatrix to Denebola, it's kind of your first stop along the way. Now, by the way, these finest NGCs are just a small sampling of the many dozens of galaxies in the neighborhood. If I bring up, as you can see here, so, you know, it could be a little bit tricky to find one from the other. I'm going to try to guide you to the right one. So this galaxy is just center it up here. Now, again, Stellarium doesn't always have a photo for the galaxies, so you can bring up the Deep Sky Survey button at the bottom here, and that'll reveal a DSS image of it. And I'm going to turn off the stars here so you can see what it looks like. This is a nice special lenticular galaxy. It's one of the flattest galaxies that we know of. Now, it's edge-on orientation, and because there's no dark dust, as sometimes these galaxies have, make this object bright enough to see in, you know, medium size and larger telescopes. So you get that nice bright slash of light that makes it a bit easier. It's in the same field of view as NGC 4754. And this object itself, the 4762, was discovered by William Herschel back on March 15th, 1784, and he classed it as number 75 in his type 2 galaxies. So as I said, it's on that line connecting Vindemayatrix to Denebola, but only 2¼ degrees west of Denebola. So if I kind of open up this field of view here, I think I can, let me bring up the stars. So there you can see there's Vindemayatrix, and it's really only a couple of, you know, 1½ degree fields of view to the west of that. On your way, you're going to pass a nice double star. This is Struve 1689, so you can sort of stop and enjoy that double star on your way to it. And of course, as all with these galaxies, you want to use averted vision. You want to use, again, a range of different magnifications. So start, you know, locate it with a lower power, but then magnify more as your conditions permit. And you're going to note its shape, its orientation. See if you've got a bigger telescope, see if you can see that it's not a perfect plane. Look at the way these two ends are a little bit bent. So that's interesting. And you've got some nice field stars as well to take note of. So we want to describe its core, describe how far you see the disk extending, especially if you have a bigger telescope, and don't forget to, you know, look at its neighbor when you're still in the neighborhood. It's about 64 million light years away. All right, let's wind back a little bit. I'm just going to bring this back here. So now we're going to go further from Vendomatrix. We're going to go to NGC 4526. So you can, you can star hop if you want to from 4762, or you can just make your way to 4526.
Chris, somebody's asking, are you heading east there, basically? This is on the east side of Vendomatrix.
Yeah.
Yeah.
So in the spring evening time, you're essentially going to the upper right. You're going west, right? In terms of celestial coordinates. So Denebola is west of Vendomatrix. Is that what you mean?
I think that's what they were shooting at. Yeah.
Yeah. Yeah. So from Canada or the Northern Hemisphere, you're essentially going to the upper right from Vendomatrix. Yeah, no problem. All right, here's my 4526. Here we go. So this is actually, again, let me just bring up the picture here again. Here we go. So this is another one of those lenticular galaxies. It shares a low power field with another finest NGC, so you get 2 for 1. If I open up the eyepiece view here, you can see you've got both finest NGCs in the same field of view. So you're going to want to log both of these at the same time. And you've also got Messier 49, which is just sitting down here. So if I can make this move. There we go. So if you've got about a 1.5 degree field of view, you can get M49 and the 2 finest NGCs in the same field of view at the same time, if you want to. I've heard reports that 4526 is bright enough to be seen with binoculars on a very good dark sky. So any size of a telescope will work as well. Discovered by William Herschel back on April 18th, 1784, number 31 of his class 1. He also picked 4535 as his number 38 in his class 1. The best way to find it is probably to get yourself to M49. And what you can do is, let me just bring this back here. So I'm just going to bring up some stars here. So rather than use Vendomatrix and going to Denebola, find Minalauva. This is the Delta Virginis. And from here, it's pretty much exactly on the line to Denebola. So you can, I think it's 40, what did I say? 40% of the way. So less than halfway between the 2 stars. So that's another way of doing it. So if you can see M49, you're away to the races, but otherwise you can sort of aim your finder 40% of the way from Minalauva to Denebola. What I did is another way you can do it is you can start at Vendomatrix and you can hop to some of these brighter stars like Rho, and again down to this. And when you're in the right neighborhood, you're going to see a couple of nice bright field stars kind of flanking it. So we've got these magnitude 6.7 and 6.9, so relatively prominent stars, and you want to look between them for the galaxy. Again, you want to use your averted vision. Just zoom in with a telescope view here. I'll bring up the deep sky image, turn off the stars so you get a sense of what it looks like. So a neat little kind of trio of the galaxy between the 2 stars. Vary your magnifications with this one. Notice the bright core. See how much of the halo you can pick up. Look for any asymmetry in it. So I'll just zoom in here and see the asymmetry in it. And the reason I mention the asymmetry is because the stellarium image I'm showing you doesn't really do justice to this galaxy. After you've observed it, go look up a Hubble image. You'll be impressed. This one's about 40 million light years away. All right, now the 4535, its name is the Lost Galaxy of Copeland, or the Lost Galaxy. It's about a magnitude, almost magnitude 10, 9.73. It's a medium-sized, kind of grand design spiral with a slight bar. So the barred spiral galaxy. And it was discovered by William Herschel on December 28th of 1785. You might be able to see it in a 4-inch telescope, at least the core anyway, under very dark skies. It'll certainly be visible in a bigger telescope than that. I recommend viewing it at the same time as the previous one as well.
Yeah, somebody's asking if you could see it with a 254mm scope using 70x.
250mm.
254mm telescope using 70 magnification.
So that's a 10-inch, right?
Yeah.
Yeah, no problem. I don't think there'd be any problem with that. Yeah. Yeah. So you're well ahead of the game if you've got a 10-inch telescope for any of these NGCs. Again, finding it the same way you found the other object because they're sharing the same field of view. I did mention.
Yeah, I guess what he wants to know with a telescope question is, can I see the arms with a 10-inch telescope?
Ah, can you see the arms? So that was my point. If you have a bigger telescope, see if you can see the S shape. I think you've got a very good chance of picking up the S shape if your transparency that night is good and your sky is very dark. But that would be certainly something that I would suggest looking for if you've got the bigger scope. Yeah. Yeah, you anticipated my notes. I was going to mention. Nice. All right. What's up next? Got a bit of a challenging one next, I found. And that was the Siamese twins. So I'm just going to wind back and show you where these are. All right. So now we're back on the line from Vindemayatrix to Denebula. And we're going to go to NGC 4567 and 4568. So that's, here we go. 4567. Where am I here? So this one is a pair of unbarred spirals discovered by William Herschel on March 15th, 1784. He called these number 8 and 9 of his class 4 objects. This one's going to need at least a 6-inch telescope to see it, and dark skies. That'll show you a kind of a fuzzy smudge. You might be able to detect that it's not a regular shape in that size of a telescope, but you definitely want a bigger telescope if you want to see the fact that it's kind of a V-shaped pair of galaxies interacting or colliding. It's about 1 degree south of the line from Vindemayatrix to Denebula. So if you've got a wide field eyepiece, then you should be pretty safe just to nudge the telescope a little bit to the south of the line, and you're going to go about 1/3 of the way. So kind of aim your telrad or your finder scope about 1/3 of the way between the stars, and then nudge it a little bit to the south, and you should be able to pick up the spot you need. Also, there's a bright Messier here that might catch your eye first. Messier 58 is right in the neighborhood as well, so that's something you could sort of target first and then navigate from there. So what I noted when I was looking at it was this neat kind of ring of shepherd stars. Maybe there's an asterism for us in there, Charles, I don't know, but this kind of a neat little shepherd or audience to these stars kind of doing their galaxies doing their thing. I guess we could get a little colorful here, but we don't need to. So yeah, you want to use it for division, try to see if you can see the shapes. You might be able to pick up, the individual halos, the 2 different halos, and note those cool, interesting field stars. And there are other galaxies in the neighborhood as well. So, you're bound to see some other ones if you look around. Now from here, I recommend getting yourself to Markarian's chain. So let's bring up the whole picture. Markarian's chain is, I wrote it up in the final Sky News magazine, if you've got a copy of that handy. And you want to go midway between Vindemayatrix and Denebula, just aim your finder or aim your telescope as close to halfway between those 2 stars as you can. Zoom in, and what you're going to pick up or notice is you're probably going to see the fuzzy blob of Messier 87, or hopefully you're going to see the duo of M84 and M86. And that's going to give you the beginnings of Markarian's chain, which sweeps kind of to the east and north from those two bright elliptical galaxies. And these two finest NGCs, another 2-for-1 situation, are huddled in close. And some people, obviously your telescope is going to maybe flip the orientation a little bit here, but some people imagine they're seeing a little face, the two big bright ellipticals as the eyes, a little dim galaxy as the nose, and NGC 4388 as the mouth. So let me just center this up here. 4388, here we go. So 4388 is a highly inclined spiral galaxy. It's located at that end, the one end of Markarian's chain. That makes it really easy to find. And it will be bright enough to see in most telescopes under dark skies because it's, barely inclined away from edge on. So it's nice and concentrated light. And you want to use your averted vision again. And again, try some different magnifications to see its stellar core and how much of its sort of oval lozenge you can track out to the edge of it. And obviously, as we're in the Virgo cluster, when you're here, look around, see if you can see any of these other fainter galaxies in the neighborhood as well. Pick those up as well. This one's about 4388 is about 55 million light years away. All of the Markarian's chain galaxies are about that distance. All right, so while we're in the neighborhood, we're going to head over here and sweep to the east and pick up what are called the eyes. These two galaxies form a relatively bright pair in your telescope. In fact, if you look at the surface brightness of NGC 4438, look at this. It's only surface brightness of 11.41. That's crazy bright. So that actually will make it quite readily visible in most size of a telescope. So we call those the eyes. They're discovered by William Herschel back on April 8th of 1784. And you can see if you zoom in, if your sky is good and your telescope's a bit bigger, you can note that the disk has been dramatically warped by the gravitational interactions of its neighbor and other galaxies in the cluster. That makes this galaxy an ARP galaxy. ARP's number 120 of his peculiar galaxies. So when you use your averted vision, tease out some details of it. Can you see the two cores of the two galaxies, the warped halos? And if I just simulate the telescope view, you can see that at a low power, you can easily navigate yourself along Markarian's chain, even though it's sort of flipped upside down in a Dobsonian telescope. And yeah, so I recommend once you're here, keep on going, find the rest of the chain. All right, let's come back. Got a few more to cover here. So now we've gone halfway from Vindematrix to Denebula. Now we're going to head a little bit further afield to NGC 4216. This is called the Silver Streak Galaxy, or the Weaver's Shuttle. And another one of these relatively easy to see galaxies because it's so edge on to us. Makes a bright oval. It's a real showpiece. I'm not sure why it didn't warrant inclusion in Messier's list. It's magnitude 10, surface brightness of 12. It's a really great galaxy. Highly recommend checking it out. It's also flanked by these two edge-on spirals. Look at this, one here and one here. Those are designations 4222 and 4206. So if your telescope is big enough and your sky's good, you might get all three in your view if you're lucky. So this one, 4216, was discovered by William Herschel on April 17th of 1784, number 35 on his class 1 list. And it should be visible by most any telescope. Let's see. The way I found it was I star hopped from NGC 4388. So where was mine? Well, I actually used one of the finest NGCs and I just star hopped east from there or west from there towards Denebula. You want to use averted vision, start out at low power, and then crank it up if your conditions allow to see more of the characteristics of the galaxy. This one's got a dust lane in it, so that'll affect, how fuzzy or how sharp the various edges of the galaxy are. So you want to make note of all those, see if you see the companions. Again, it's about 55 million light years away. All right, the last one up is this one down here in Southern Virgo. We're going to look at NGC 4699. Stephen O'Meara in his book, Secret Deep, I think, or Hidden Treasures, calls this the vinyl LP galaxy because he sort of thought it looked like a light glinting off an old vinyl record. So here we go. Again, Stellarium has no picture, so I'm going to bring up the deep sky survey image of it. Here we go. It's kind of like a platter. You can see there's a bright core that makes it really easy. He suggested you can see this one with binoculars, or at least detect it as a fuzzy spot with binoculars. Really, any size of a telescope should be able to pick it up with such a bright core. Discovered by William Herschel on March 3rd, 1786, number 129 of his group number 1 class of objects. And I've got it noted as being midway between 2 magnitude 4 stars. So I'm just going to turn off this and bring those into view. Let's go back here. So the star Psi and Chi Virginis. So you've got, there's Psi and there's Chi or Chi. So these are both close to naked eye stars. Definitely binoculars would see them. So that would greatly aid your aiming your finder scope. Or you can look at making a triangle with Spica and Porrima on the Corvus side. That's another way of doing it. Or you could, let's see, I have aiming your finder midpoint between Genea and, go, one of these stars. I forget which one I used. But anyway, there's a few ways you can find it. So when you're there, you want to look for another cool little asterism, this little arc, little curl of stars, this arc of stars. The middle one or the second one is a double star. That'll be neat. So that'll confirm you're in the right spot using the 2 bright ones and the little arc below. And again, you want to use, just bring up the eyepiece view here. Here we go. And here's what we're going to see. So again, this one's pretty small, so you want to increase the magnification. Just bring up my. There we go. Is it going to do it? There we go. There's the magnification at about 65x. So you want to zoom in with different magnifications, look at different aspects of the galaxy. You can see the orientation, the shape, and if you've got a big telescope, you might detect our friend with the 10-inch. See if you can see some detail or structure in the sort of the flocculent outer ring of the arms. They're sort of choppy. And this one's about 60 to 75 million light years away. And that's it for now. That's the list.
Somebody said shepherd stars. Well, yeah, stars around the object, sort of spectators, like you say. There are a whole bunch of shepherd asterisms up there. They're in Cepheus, they're in the Ophiuchus, they're in Ursa Major and elsewhere, but there aren't any shepherd asterisms that I know of around Virgo, at least not yet.
Yeah. So obviously with when you're dealing with galaxies, your telescope, your eyes, your sky all make a difference. But what's great is that if you can match up the star field, so you know you're in the right spot, then you can take a few minutes to try to tease out that faint fuzzy, maybe tap the telescope, see if you can make it wiggle, make your wiring in your brain, reveal that faint object, or just, make note of the way it looked, come back another night when it's better and try again. But yeah, we use all these tricks.
Somebody wants you to do a Hubble constant show.
A Hubble constant show.
That's what they say.
Okay. Great. Yeah, I'm happy to take suggestions. Don't mean I'm an expert, but we'll try to find somebody who is so that's fine. Great. Well, I hope everybody gets some clear skies. The weather is improving. It's not going to be great in Toronto, but folks elsewhere, and watch out for aurora. We've been getting some great shows from the sun.
Yes, somebody was saying, is asking anyone show aurora borealis on Sunday night. It was down way south on Sunday night. I didn't have a sky to see it here, but
Not here either.
yeah. Well,
Fantastic.
actually, should ask Vicky Johar from the Yukon Center what it looked like up there. She did a presentation for our center the other day on Aurora, and they've got some fabulous photos. Because they're right up there in the oval most of the time.
Fantastic.
All right.
All right. Well, that's it for today, everybody. I hope you have clear skies and luck with these, and let us know how you're doing. And definitely try them. You don't need to finish. Don't worry about not being able to finish the whole list. I guarantee you there's a lot of really fantastic gems in the finest NGCs we're looking at. Definitely worth looking at. So
All right.
keep looking up.
Thanks, everyone.